At 17,500 miles per hour, docking requires absolute precision. This is the anatomy of an autonomous docking.
In the vacuum of low Earth orbit, there is no air resistance to slow things down. Objects up here travel at roughly 5 miles per second. At that speed, you can cross the entire continental United States in under 10 minutes. One of those objects is the International Space Station, a fragile, football field-sized laboratory orbiting in a constant state of freefall. The other is a spacecraft, like the SpaceX Dragon capsule, tasked with tracking down the station and connecting a small specialized hatch directly to the ISS. To actually connect the two structures, both the capsule and the station must maintain their blistering orbital velocity of 17,500 miles per hour, while simultaneously bringing their relative speed exactly to zero. For decades, closing this final gap required human astronauts tightly gripping manual controls, adjusting thrusters by eye and feel to physically fly one massive object into another. But human reflexes have limits. A misjudged millimeter or a thruster fired for a fraction of a second too long at this velocity would easily tear through the station's hull, venting the crew's oxygen into the void. The physics demanded a new approach. To guarantee the station's survival, engineers removed manual joysticks entirely, turning a collision risk into a strictly mathematical sequence executed by computers. That autonomous sequence takes over completely at the keep-out sphere. This is an imaginary 400-meter boundary surrounding the space station, serving as an absolute safety perimeter. The moment the Dragon capsule crosses this line, it switches on its primary navigation sensors. It starts firing rapid pulses of light using LiDAR, combined with highly sensitive thermal imaging, right at the station. By measuring exactly how long for those light beams to bounce off the ISS and return, the Dragon's onboard computer translates those pulses into a live, three-dimensional topographical map of the docking port, accurate down to the millimeter. Using this continuous stream of data, the spacecraft mathematically calculates the exact thrust needed to bleed off its forward momentum, creeping steadily from 400 meters out down to a precise hold position just 20 meters away. The capsule is no longer flying blindly. It is making every steering decision based on a high-fidelity digital twin of the station it built entirely on its own. At the 20-meter mark, known as Waypoint 2, the Dragon pauses. It cannot simply coast straight forward. The docking rings require flawless geometric alignment to latch together. Achieving that alignment in a vacuum means controlling the ship across 6 specific degrees of freedom. The computer has to calculate and cancel out any pitch, yaw, or roll, while simultaneously correcting for lateral drift up, down, left, and right. To execute these corrections, Dragon fires its Draco thrusters in split-second microbursts. These tiny puffs of gas gently nudge the multi-ton spacecraft, forcing it into a perfectly stabilized corridor. Over the final few centimeters, the relative speed between the two vehicles drops to practically zero. On the nose of the capsule, a mechanical docking ring extends outward to make the initial connection. When the metal touches, we achieve soft capture. Even at a crawl, two massive objects carry tremendous kinetic energy. To prevent them from violently bouncing off one another, the extending ring's internal springs immediately compress, soaking up the impact force like a heavy-duty shock absorber. By physically absorbing that energy rather than fighting it, the engineers solved the kinetic problem. The vehicles are now tethered together, safely dissipating their momentum before they can repel each other apart. With the kinetic energy neutralized, the system initiates hard capture. The docking ring retracts, pulling the two spacecraft flush against each other as 12 motorized hooks snap firmly into place. Those locking hooks squeeze the docking interfaces tightly enough to form an impenetrable, airtight seal. This single connection keeps the deadly vacuum of space out and maintains the pressurized interior where the crew lives and breathes. As we look further out into the solar system, the stakes for this technology scale up dramatically. On a mission to Mars, the distance between planets creates an unavoidable time delay in radio signals. Light itself takes up to 20 minutes to travel one way. At that distance, sending a manual steering command from mission control is physically impossible. If we are going to build orbital gateways around the moon, or land massive cargo ships on Martian soil, the vehicles must be able to see, think, and dock for themselves. Perfecting this autonomous choreography in low Earth orbit today is exactly what makes deep space exploration possible tomorrow.